everybody. Today we'll be taking a look at Leetcode problem 236, lowest common ancestor of a binary tree. So let's get into it. Given a binary tree, find the lowest common ancestor, LCA, of two given nodes in the tree. The LCA is defined between two nodes P and Q as the lowest node T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So that's a technical term. Let's see what that actually means. In this binary tree here in example 1, we are looking for P equals 5 and Q equals 1. So P equals 5 and Q equals 1. In this case here, we are going to find 3, because 3 is the lowest common ancestor that has both 5 and 1 as a descendant. In example 2 of P equals 5 and Q equals 4, the output here is going to be 5, because 5 is a descendant of itself, and it has 4 as a descendant to its right. And that part, a node being a descendant of itself, is noted here, and that's why the example was provided. So how do we approach a problem like this? Let's imagine we had some variable called res, right? It's a return value, and it's currently equivalent to none. And what we want to do is we want to travel down this tree both to the left and right, and then at each node, we want to look whether the left and right tree, there is a descendant that is P or Q, or the root itself is 1. The minute we find such a node, we make our res be equivalent to that node, and then once we get higher up in the tree, we now know we had already found that node, so we shouldn't replace it. So what this means here in a practical example is for 5 and 4, for example, P equals 5 and Q equals 4, once we come down here to 5, well, we found 5 because P equals 5, and that's the root itself. And then if we search to the right and we find 4, okay, so at node 5, we have found 5 and we have found 4. So now we replace our return value to be this node right here. Then once we go back up to 3, we can then see that, hey, our return value already has a value. So even though we find both P and Q to its left, we should not replace that value. So right now, the way this is looking, this is going to be an n-squared approach, where at every node we look all the way down, we come back up, and we travel to the other nodes. And it also wouldn't work in this manner either, because if we had done it this way of looking at node and looking down, then what can happen is when we start off at the first node, which is 3, and we look down, it's going to return as true, as 5 and 4 are descendants of 3. And currently our return value is none, and we're going to update it. So in this order, it would not work. So what we want to do actually is we want to recursively travel all the way down to the bottom of the tree. And each node, we want to return whether we find P and Q. And if we find P and Q, we return that value to the node above. So example here, this would return false and false because we did not find P or Q at 7. We get back up to 2. So on the left-hand side, it's false and false. On the right-hand side, it's going to be false and true, because even though we didn't find P, we did find Q. So right now, 2 has not found P, but has found Q. Then when we look at 5, on the left-hand side, it's going to return false and false, because no P and Q is found. On the right-hand side, it's going to return false and true, because it did find Q before. And then because this node itself is P, so we found P at the node, we found Q to its right, and now we have found both P and Q. And now we're going to update our return value to be this node here, and then once we return from here that we found both P and Q, even though node 3 has both found P and Q, it will not update the return value because we had already updated it with another value. So let's get started coding this solution. So like we had mentioned, the first thing we want is we want to have a return value that we first start off as none. And then let's call our helper function define DFS, because we're going to do a depth first search here. And non-local res, this just means that whenever we refer to res, we're referring to a variable outside of the scope of this function. And then let's have a base case. If the current root we're looking at is null, so if not root, and then we want to return false and false. This is because a null root, by definition, right, we're not going to have found P and we're not going to have found Q, so we return false and false. Then what we want to have is left P and left Q. right? So we want to search for P and Q on the left, right? So let's recursively call our function to the left. And then we want to search for it to the right, right P and right Q equals DFS root dot right. And now these calls are going to recursively traverse down the left and right accordingly. And this is what's going to allow us to build it from the bottom up. And then let's call this variable found P. So what does it mean to have found P? Well, found P means three scenarios, right? Either it means the root node itself is P, right? So root equals P, or it means we have found it on the left side, so left P, or we found it on the right side and right P. So this found P will be true if any three of these scenarios are true. Either the root itself is P, either on the left hand side it's P, or on the right hand side we found P. Now same idea here for Q equals root equals Q, or left Q or right Q. So now we have these two Boolean variables, found P and found Q. And what we want to do is on the first instance of us founding P and us finding Q, we want to update our value res here to be the node we are at. So because we are calling these values here in the beginning, we know we are building from the bottom up. So the first time we find these is going to be the first time that res is none. So we're going to say if we have found P, right, and we have found Q, and res is equal to none, right? Or this can be simply said as and not res, right? Because if res doesn't exist or it's null, it's going to return false. And if you say not false, it's going to be true. Then we just want to update res to equal root. And root's going to be the current node we're on. And then finally, to incorporate the logic of returning P and Q, where we did here, we just return whether we had found P at this node and whether we had found Q at this node. And this completes our function. So now all we have left to do is simply call our function, DFS root. This is going to recursively traverse down the tree. And at the end of it, we are going to have our res node, or aka the node which has both P and Q as descendants. So we just return res. So let's submit this. And there you go, we have completed the question. Hopefully you guys found that useful and educational. If you do, please consider liking and subscribing, and see you guys next time.